Thank you, Wayne, and the PFA organization for asking me to reprise this presentation given just a few days ago at a Foam Expo Lunch and Learn event that I did for the resin aromatic polyether polyols. I'm Steve Crain. I come from Bakelite Synthetics. I'm a business development leader. Although I've had a 35-year career with a company called Dow Chemical, I am now with Bakelite Synthetics and have been with the company for a couple of years. Much of my experience has been in rigid foam, so you'll probably take note that I'll stumble a few times as I go through the flexible foam activities that we've been involved in our labs, particularly in our labs in our foam labs in Italy. For those of you who have heard the name Bakelite but have not heard of the company name Bakelite Synthetics, Hexion's phenolic specialty resins, European Forest Products Division, and Hexamine businesses were sold to Black Diamond and Invest Industrial, and we became a standalone company on May 1st. And the Bakelite Synthetics is a nod to our traditional products that we sell with the Bakelite brand, but also to the innovation that is going on in this business over the last number of years. The presentation is reducing odors from flame retardants and flexible foam. So is it possible in this particular activity to reduce, for example, TCPP, halogenated flame retardant, with some vapor pressure, and therefore affect the odors from the flexible foam? And so that's the investigation that we're moving forward with. Our concern has been mostly in this presentation is reaction to fire and mechanical properties for those systems. Now back to Bakelite. If you remember, Bakelite is essentially highly aromatic systems. Let me see if I can transition the slide. There we go. Bakelite are high aromatic systems. We have been selling highly aromatic polyols to the polyurethane industry for some time now, but we have decided to expand the list of particular of polyols to be able to address many of the segments in the polyurethane industry. We have been mostly focused on rigid polyurethane foam and some case applications, particularly adhesives and elastomers. But we began experimenting with our materials in flexible foam systems to determine if we can influence positively the reaction to fire properties of the foam without damaging the typical flexible foam properties, and therefore allow freedom for the formulator to make adjustments either in the amount or the type of fire retardant to affect odor in the system. So when we first got into the market of polyols for the flexible foam, well, for the polyurethane foam industry in general, we began thinking about the types of materials that we can provide: aromatic polyols, aromatic polyether polyols, and an aminated aromatic polyether polyols. I'm going to focus primarily on the aromatic polyether polyols, in other words, the polyols that have been alkoxylated. And the real focus is on reaction to fire. We're interested in seeing if we can use our highly aromatic materials known for phenolic foams, known for fire-resistant composites. Can we improve the fire resistance of foam systems, including the flexible foam that we'll be talking about today? So that's the main structure of the presentation today. We have a number of case studies associated with what people have been interested in, what samples they have taken into their shop, made foam or adhesives, and then tested those materials and seeing what effect, seeing if what they were seeking is true. So for example, you can see in this particular instance, on the left side, I have a whole bunch of 1 through whatever numbers. Those are the various customers. You can see their applications that they have considered for the materials. You can see the products that they evaluated, and then what were they looking for with our particular materials? What was their pain point? You can see in a lot of cases, improved reaction to fire and mechanical strength stand out tremendously as what people are seeking with our materials. And so these are successful. These are check marks showing the success that they have had in evaluating our materials. Notice that there are no flexible foam case studies at this particular point, although we are working with several customers in the flex foam industry. So right now, I'm going to take a step back and say, okay, why aromatic polyols, particularly from Bakelite synthetics? And as you can imagine, as I talked about phenolic foam and composite systems, resold, Novalax foam, this is Bakelite synthetics bread and butter. And you can see why. The aromatic polyols that we have are in the 70+ range in terms of the percent aromaticity. The aromatic polyether polyols that I'm going to talk about today range from 20 to almost 50% aromaticity. And the reason that is important for our particular discussion is, can I form char even in a highly non-aromatic system? If I can just add our materials in a small amount, using them as FR additives in truth, will I affect the char formation and therefore reaction to fire? So in the rigid foam industry, it's pretty straightforward for us now. We've got so much data, both customer and our own internal data, showing the reaction to fire when we add a small amount of our materials. You can see in this particular presentation, this particular slide, it's a rigid foam system. We took out the aliphatic polyether polyol, left in more or less the aromatic polyester polyol, and introduced some of our polyols to these systems, and you can see there's a significant drop or improvement in reaction to fire, drop in the relative height of the flame. This is the DIN 4102 test, or B2 test, as we tend to call it, for these rigid foam systems. So now I'm going to move into fairly quickly into why we would want to do this and can we do it for flexible foam. And the goal is to generate a perfect char. Now, if we could generate graphene, that would be great. We're probably not going to be able to do that, but we would like to condense a lot of polyaromatic hydrocarbons and then foam that char and use that char to protect as much as possible the foam underneath. So the question for flexible foam is then, can I take a small amount of our resonance materials and dose it into a flexible foam formulation and see an improvement in reaction to fire and be able to make reasonably good looking flexible foam with the mechanical characteristics that are needed? So this work started in a sense, I believe, early part of this year. So we're pretty new into this particular effort. Now you can see here's a generic foam formulation that I've got various references that you can pull from. And this is what we use to begin our evaluation. The items in blue, the polyol, the water, silicone surfactant, those are the materials we chose to include in our formulation. A very simple formulation, not very elegant, something that's been done in the past, as you can see from the references. We know it will make foam. We're going to start dropping in some of our material. And so for these particular systems, we just took a small amount of various of our aromatic polyether polyols. You can see PL91203, PL91507, PL92450 in small quantities, 10 parts out of 100 or 20 parts out of 100, drop them in to see what would happen with our materials. Would the mechanical properties be maintained? Would the reaction to fire actually be improved? Well, one of the first things that we had to do is, of course, make some foam, and we wanted to check to see if our reactivity was acceptable with respect to the foam rise profile. And at first, you can see that the control is a relatively slow foam rise profile. Our materials, when we drop them in, have has a somewhat faster rise profile. Now, looking at the products that we're going to be talking about today, you can see that in the table in the right-hand corner, you can see that the original polyol has a functionality 3 and a hydroxyl value of 56, a very standard, very common polyol for this type of system. So the hydroxyl equivalents in that system are very low, and the hydroxyl type is secondary. The PL91203 has a high hydroxyl equivalent because the hydroxyl value is much higher, and we're considering primary hydroxyl type. Now the PL91507, because of its lower hydroxyl value, has a lower number of hydroxyl equivalents than the other resonance materials, but it also has a hydroxyl type that is primary alcohol. The PL92-450, however, it has a similar hydroxyl value as the PL91-203, so higher hydroxy equivalent versus the original polyol, but now we have secondary OHs for those systems. So you can see that's why the reactivity is a bit faster for our materials, either high hydroxyl equivalents or the hydroxyl type is primary. We did do a small amount of evaluations, just a very small adjustment in 10 catalysts, and you can see they almost overlap with the control at that particular point. So these materials are fairly easy to modify the rise profile. Here's one of the formulations where we just put 10% of the polyol is our particular materials, the 203, 507, and 450. You can see the mean catalyst, the 10 catalyst that's used, the silicone surfactant at 1 part. We're using TCPP at 18 parts for this particular formulation. The goal, of course, is to see what happens when we reduce that. But I just wanted to show you the type of foam properties that we get. You can see the closed cell content is about the same, very low. The foam characteristics that were prepared are very similar with respect to each other. Compressive strength, recovery after 24 hours, all those properties were not negatively affected at 10 parts of material. Same thing with some of the materials, we actually introduced 20 parts, and we can see that, again, the properties are unaffected. We also began to reduce the TCPP. So we went a little over 20% reduction in the TCPP because we figured it has to be a fairly large reduction in TCPP to affect the odor of a system, considering that TCPP has a relatively low vapor pressure, so it must take a lot to create any kind of odor. The only delta we saw with this particular system is the reference that we're using versus the 18 parts of TCPP began to split. So we were able to cut some samples for at least reaction to fire testing, but we were struggling with the material splitting, as opposed to the materials with our materials did not exhibit splitting for those systems. Now we have to test reaction to fire, and being new in the system, I have done new with flexible foam. I wasn't sure exactly which would be the most reasonable reaction to fire test to choose. I could do a UL94HB, sort of like, what is it, the MVSS 302, or I could do a cone calorimetry, I could do a limited oxygen index, DIN 4102. It seems that these materials are somewhat used on occasion for each one. We chose to do our reaction to fire testing with the cone calorimetry, just because there's degrees of freedom in terms of adjusting the heat flux to the system. In other words, how much heat is going to the system. You can see the cigarette at 40 to 65 kilowatts per square meter. So we thought, well, we can use the cone calorimetry and pick a number, and it seemed that 25 was a reasonable number based on what we were reading, and we'll go ahead and test everything at 25 kilowatts for those systems. Yeah, we did do some evaluations, UL94HB. We struggled at cutting thin enough foams. For example, the MVSS test is supposed to be 13 millimeters thick, and you can see ours were pretty thick samples, so useless test as we found out. All right, so that's our dirty laundry, so to speak. So what happens when we use the cone calorimetry, which we use quite a bit in our industry, the rigid foam industry? It's a great tool to be able to communicate across product lines and across segments, whether it's appliance or slab stock or flexible face, rigid face panels, and so on. So in this particular instance, we're looking at primarily the 10 and 20 parts of PL91-203. What happens if we add PL91-203 or PL92-450 at 10 parts, and then the other ones we'll just pick, because they're lower viscosity, we'll pick 20 parts each and just compare that with the references. The first reference is at 18 parts of TCPP. The second reference is at 14 parts of TCPP. not only did we have splitting with those materials, but you can see the reaction to fire decreased. In other words, that it got worse at the 25 kilowatt per square meter heat flux. The PL92-450, introducing it into the formulation at 18 parts, automatically began to improve versus 18 parts of PCP in the reference. Similar to the other material, the PL91-203 and the PL91-205 all seem to improve further with the introduction of our resonance materials. And as a matter of fact, as you can see from the bars that are showing here, starting with the orange bar, when you go from the 19 to the 14 parts of PCP, we not only did not see a degradation of the total heat release, but we actually seem to see a consistent slight improvement. Not something that I would take to the bank, but certainly a consistent improvement. So we were quite encouraged when we saw these materials and are suggesting these resonance high aromatic materials for your consideration as additives, not as a replacement for your polyols, but as an additive in 5 parts or 10 parts or 15 parts in your particular system to be able to either reduce the fire retardant, to be able to improve the odor of a particular system, or maybe you want to swap to a new fire retardant, for example, going from halogenated to non-halogenated, but you're concerned with the reaction to fire. Use a small amount of our material and you should be able to see an improvement in reaction to fire. As a matter of fact, for our particular systems, we actually sell a number of them in trialpha phosphate because our customers have asked us to do that. In other words, provide them with binary blends for their personal convenience. You can see the aromaticity in general for these materials. They're ranging from 24 to 33%. And of course, the reason we're able to maintain mechanical properties, you can see the functionality is commensurate with the polyols that are typically used in flexible foam. Finally, just to summarize, again, the question is, will the addition of small amounts of resonance improve reaction to fire? And we can say yes. Replacing 5 to 20 parts of the resonance polyol at an additive level, in other words, other resonance aromatic polyether polyols will enhance the reaction to fire, not just maintain at even lower levels of fire retardant. At least with this particular system, of course, you would want to consider your own system and do your own testing to ensure this would happen. Foam rise profiles were easily adjusted with small adjustments in tin. The flexibility and mechanical properties were unaffected with the introduction of the resonance materials, even when we took out some PCPP, which was a bit of a surprise because you can imagine the system is getting a little more viscous because of that. And the reduction of about 20% in the presence of polyols did not affect that foam property. Thank you for listening to this presentation. If you have questions, I will entertain them at this particular point.